The gym is a physics playground. Each and every movement, basic or advanced, involves physics and forces in some way. Whether it be a pushing force, a pulling force, a gravitational force, or a tension force, examples of physics permeate the gym floor. We will be performing exercises explaining how these exercises use physics to achieve their movements and calculating the work done on the system during those movements. In this example, the system is the hands, the bar, and the weights on the bar. The forces being exerted on the system are the pushing force, the normal force, and the gravitational force. Throughout the entire movement, the gravitational, normal, and pushing forces are always in action. As the bar moves downward, the gravitational force is stronger than the pushing force, causing the downward movement. As the bar moves upward, the pushing force is stronger than the gravitational force, causing the upward movement. In this example, the system is the weights, and the external system is the person, the pulleys, and the cables. The forces in action are the pulling force, which is the same as the tension force when ignoring friction, and the gravitational force. Energy is transferred from the person, aka the external system, to the weights through work done by the pulling force. The combination of two pulleys change the direction of force from horizontal to vertical. How much work is being done on the weights during the cable row? It is given that the weights equal 68 kilograms, the distance is 0.25 meters, and acceleration equals 0 meters per second squared because it is moving at a constant motion. To be determined, work! Net force equals mass times acceleration. We know that the mass is 68 kilograms and the acceleration is 0 meters per second. Therefore, net force equals 0. F net equals F pull minus Fg. And since we know F net equals 0, we also know that F pull equals Fg. So we must first find Fg. So we know that Fg equals 68 kilograms times negative 10 meters per second. So Fg equals negative 680 newtons. Therefore, F pull equals 680 newtons because F net equals 0. Now we can finally calculate work. Work equals force times distance. So 680 newtons times 0.25 meters, which equals 170 joules on the weights. As a measure of accuracy, we can also calculate work done through energy. So W equals change in kinetic energy plus change in potential energy. To find kinetic energy, we use Ke equals 1/2 mass times velocity squared. So kinetic energy equals 1/2 times 68 kilograms times 0.25 meters per second squared. And this equals 2.125 joules. To find potential energy, we must multiply mass times gravitational constant times the distance, or height. So this is 68 kilograms times 10 meters per second squared times 0.25 meters. This comes out to be 170 joules. And work equals change in kinetic energy plus change in potential energy. So work equals 2.125 joules plus 170 joules, equaling a total of 172.125 joules on the weights, which is just about the same calculation that we got initially. Whew! We did it. It was a lot of calculation for such a simple movement. In this example, the system is the hands, the bar, and the weights on the bar. The forces being exerted on the system are the pulling force, the normal force, and the gravitational force. As the hands move the bar upwards, the pulling force is greater than the gravitational force, allowing for upward movement. As the hands let go of the bar, the only force acting on the bar is gravity, causing the bar to move downward at free fall, accelerating at 9.8 meters per second towards the center of the Earth. Once the bar reaches the ground, the bar comes to rest, and the system is reset. Also, a little pro tip, don't drop your weights like this when you're actually at the gym. It's kind of annoying.